The solar system sits on a shelf somewhere, bound in a thick binder with worn corners and coffee stains on the cover. If you flip it open, you won't find tales of cosmic catastrophes or dramatic explosions. Instead, you'll see page after page of tables, diagrams, and maintenance logs. The kind of documentation that keeps a very old, very reliable office running smoothly. Tonight, we're simply going to read through it, section by section, learning how our local neighbourhood operates not through spectacle, but through schedules, checklists, and the patient work of gravity keeping everything on track. The first page inside the binder shows a simple block diagram. At the centre sits one star, labelled with its mass, radius, and energy output. Radiating outward in roughly concentric rings are 8 major planets, their orbits marked with average distances and period times. Smaller annotations indicate asteroid populations, distant icy bodies, and the occasional comet on a long elliptical path. Off to the side, a legend explains the basic parameters: masses measured in kilograms or relative to Earth, distances in astronomical units, temperatures in Kelvin. Everything is presented matter-of-factly, the way an engineer might document a power plant or a warehouse manager might track inventory. There are no exclamation points, no warnings about impending doom, just measurements, recorded and cross-referenced, waiting to be consulted whenever someone needs to know how things work around here. Turn to the next section, and you'll find the Sun's service record. It's listed as the primary energy source for the entire operation, a main sequence G-type star currently about halfway through its expected operational lifetime. The entry notes its mass at roughly 2 × 10 to the 30th power kilograms, its radius at about 700,000 kilometers, and its surface temperature hovering near 5700 Kelvin. Deep in its core, hydrogen nuclei fuse into helium, converting a tiny fraction of mass into energy, according to a well-understood equation. This process releases photons that work their way outward over thousands of years, eventually streaming into space as sunlight and carrying with them the solar wind, a flow of charged particles that fills the local environment. The operations file treats the Sun as a power plant with a known budget. It produces about 3.8 × 10 to the 26th watts, a figure that has remained stable within small variations for billions of years. This steady output drives nearly everything else in the system. Planets absorb sunlight and radiate heat. Solar wind shapes magnetic fields and pushes comet tails. Even the orbits themselves, while primarily governed by gravity, are influenced at the margins by radiation pressure on small particles. The manual notes that the Sun has already consumed roughly half of the hydrogen in its core, meaning it has operated for about 4.5 billion years, and is expected to continue at current levels for another 5 billion or so. After that, the entry includes a note about eventual expansion into a red giant phase, but that section is marked long-term decommissioning, not relevant to current operations. What keeps everything in place isn't just the Sun's energy, but the fundamental office policy that governs the entire system: gravity. The manual dedicates several pages to explaining this rule in plain language. Every object with mass attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It's a simple relationship written in a short equation, and it applies universally. The Sun, being by far the most massive object in the system, exerts the dominant gravitational pull on everything else. Planets, asteroids, comets, and dust grains all respond to this force by moving in paths determined by their initial positions and velocities. The beauty of this policy, from an operational standpoint, is that it requires no ongoing enforcement. Once objects are set in motion with particular speeds and directions, gravity alone dictates their future paths. If a planet is moving at just the right speed for its distance from the Sun, it will trace out an ellipse, returning to the same points over and over. If an asteroid finds itself at a certain distance with a certain velocity, it too will follow its assigned orbit, neither spiraling inward nor drifting away, unless some external perturbation changes its trajectory. The manual describes this as a self-maintaining system. After the initial configuration was established, the rules of motion took over, and the solar system has been running on autopilot ever since. Flipping forward, you reach the planetary appointment book. Here, each planet gets its own entry, laid out in rows of a scheduling table. Mercury, closest to the Sun, orbits at an average distance of about 0.39 astronomical units, roughly 58 million kilometers. Its orbital period is listed as 88 Earth days, meaning Mercury completes a full circuit around the Sun in less than 3 of our months. The entry notes that its orbit is slightly elliptical, with an eccentricity of about 0.2, so its distance from the Sun varies noticeably over each lap. Still, the appointment repeats like clockwork. Every 88 days, Mercury returns to the same position relative to the Sun, ready to start another loop. Venus comes next, orbiting at 0.72 astronomical units, with a period of 225 Earth days. Its orbit is nearly circular, one of the most circular in the system, with an eccentricity close to 0.01. Earth follows at 1 astronomical unit by definition, taking 365.25 days to complete its orbit. Mars orbits farther out at 1.52 astronomical units, requiring 687 days for a full revolution. These inner planets form the first cluster of appointments, all relatively close to the Sun, with periods measured in days to a couple of years. Beyond Mars, after a gap occupied by the asteroid belt, the giant planets take over. Jupiter sits at 5.2 astronomical units, its massive bulk taking nearly 12 Earth years to complete one orbit. Saturn, at 9.5 astronomical units, needs about 29 years. Uranus, at 19 astronomical units, takes 84 years, and Neptune, the outermost major planet at 30 astronomical units, requires roughly 165 years to circle the Sun once. The manual presents these as recurring calendar entries stretched across vastly different timescales. While Mercury zips around hundreds of times in a human lifetime, Neptune has completed barely more than one full orbit since its discovery in the mid-1800s. Yet both follow their schedules with the same reliability, neither early nor late, because the gravitational policy doesn't care about speed, it cares about the balance between distance and velocity. Each planet also has a rotation entry, describing how long its day lasts. Mercury rotates slowly, taking 59 Earth days to spin once on its axis, which means it completes 3 rotations for every 2 orbits, a resonance locked in by tidal forces from the Sun. Venus rotates even more slowly and in the opposite direction from most planets, with a day lasting 243 Earth days, longer than its year. Earth rotates once every 24 hours, a rate that shapes our experience of day and night, the rhythm of temperature changes, and the pattern of winds and ocean currents. Mars has a similar rotation period, about 24.5 hours, so a Martian day feels much like an Earth day in length. The giant planets spin much faster. Jupiter, despite its enormous size, rotates in less than 10 hours, creating powerful atmospheric bands and storms driven by rapid circulation. Saturn takes about 10.5 hours, Uranus roughly 17 hours, and Neptune just over 16 hours. These rotation rates appear as shift schedules in the manual: how long each planet's surface or cloud top spend facing the Sun, how quickly heat redistributes, and how rotation interacts with atmospheric dynamics. For the gas giants, rapid rotation flattens their shapes slightly, making them bulge at the equator. For rocky planets, rotation influences everything from magnetic field generation to the thickness of the atmosphere a given spot can hold onto during the hot part of the day. Moons add their own rotation entries to the subsystems. Many large moons are tidally locked, meaning they rotate once per orbit and always show the same face to their parent planet. Earth's moon does this, completing one rotation every 27.3 days, the same as its orbital period around Earth. Jupiter's large. Moons, Io, Europa, Ganymede, and Callisto, are all tidally locked to Jupiter. This synchronization happens over time as tidal forces from the planet gradually slow the moon's rotation until it matches the orbital period. The manual logs these as stable configurations. Once tidal locking is achieved, the moon's rotation and orbit stay synchronized without further adjustment. No orbit in the system is perfectly circular or perfectly flat. The operations manual includes entries for orbital eccentricity and inclination, small deviations that are well within acceptable tolerances. Eccentricity measures how stretched an orbit is. 0 means a perfect circle, and values closer to 1 mean increasingly elongated ellipses. Most planets have eccentricities below 0.1, keeping their orbits nearly circular. Mercury's 0.2 eccentricity is the highest among the major planets, causing its distance from the Sun to vary from 46 million to nearly 70 million kilometers over each orbit. Earth's eccentricity is only about 0.02, so our distance from the Sun changes by just a few percent throughout the year, not enough to drive the seasons, which are caused by axial tilt instead. Inclination measures how tilted an orbit is relative to a reference plane, typically the ecliptic, which is defined by Earth's orbital plane. Most planets orbit close to this plane with inclinations of just a few degrees. Mercury again is the outlier, with an inclination of about 7 degrees. These small tilts mean the planets don't all line up in a perfectly flat disk, but the deviations are minor. The system's architecture allows for these variations because they remain stable over long periods. The manual notes that eccentricities and inclinations can oscillate slightly over millions of years due to gravitational interactions among the planets, but these oscillations stay within safe ranges. There are no runaway increases, no sudden flips in orientation. The current values are logged, and the expectation is that they will continue to wobble gently around their present averages for billions of years. Between Mars and Jupiter lies a broad zone catalogued in the manual as the main asteroid belt. This region, spanning roughly 2 to 3.5 astronomical units from the Sun, contains hundreds of thousands of rocky bodies ranging from tiny pebbles to objects hundreds of kilometers across. The largest, Ceres, is now classified as a dwarf planet, with a diameter of about 950 kilometers. The operations file describes the belt as an inventory shelf, a place where material that might have formed a planet instead remained fragmented, likely due to Jupiter's gravitational influence preventing the region from coalescing into a single large body. The total mass of all objects in the asteroid belt is estimated at only a small fraction of Earth's mass, perhaps 3% or so. Despite the popular image of a dense debris field, the belt is mostly empty space. The average distance between asteroids is vast, measured in hundreds of thousands or millions of kilometers. Spacecraft passing through the belt don't need to dodge and weave. They travel through open space, occasionally targeting a specific asteroid for study but otherwise flying unobstructed. The manual's occupancy patterns note that asteroids are concentrated in certain orbital zones and sparse or absent in others, a distribution shaped by orbital resonances with Jupiter. These resonances appear as special entries in the belt section. A resonance occurs when an asteroid's orbital period has a simple numerical relationship with Jupiter's period. For example, an asteroid at a distance where it orbits the Sun 3 times for every time Jupiter orbits once would be in a 3-to-1 resonance. Over time, repeated gravitational tugs from Jupiter at the same points in the orbit can either stabilize or destabilize the asteroid's path. Many resonances are destabilizing, creating gaps in the belt known as Kirkwood gaps. Asteroids that wander into these zones get nudged onto different orbits, some eventually crossing the paths of the inner planets or being ejected from the system entirely. The manual marks these gaps as cleared zones, long-term occupancy not viable. Other resonances, however, can be stable, allowing asteroids to persist in those locations for billions of years. Jupiter's gravitational influence extends beyond shaping the asteroid belt. The giant planet hosts its own populations of co-orbital companions called Trojan asteroids. These objects share Jupiter's orbit but don't collide with the planet because they occupy special gravitational parking spots ahead of and behind Jupiter, located at points known as Lagrange points. Specifically, the L4 and L5 Lagrange points form stable regions, where the combined gravity of the Sun and Jupiter creates a balance that allows small bodies to remain in place relative to Jupiter as both circle the Sun. The operations manual includes a sidebar on Trojan swarms, noting that Jupiter has several thousand known Trojans, with the leading swarm at L4 and the trailing swarm at L5. These populations are stable over long timescales because objects at Lagrange points experience restoring forces if they drift slightly. Move a bit away from L4 or L5 and gravity gently nudges you back toward the equilibrium position. Other planets also have Trojans, though in smaller numbers. Mars, Earth, Uranus and Neptune all have known Trojan companions logged in their files. The manual treats these as shared lanes in the system, where multiple objects can coexist in the same orbital path without risk of collision, maintained by the geometry of gravitational forces. Moving outward past Neptune, the binders pages describe the Kuiper Belt, a vast region of icy bodies extending from about 30 to 50 astronomical units from the Sun. This cold storage area contains countless small objects made largely of frozen water, methane, ammonia, and rock. Many of these bodies are remnants from the solar system's formation, preserved in the deep freeze of the outer reaches where temperatures hover just tens of degrees above absolute zero. The largest known Kuiper Belt object is Pluto, reclassified as a dwarf planet, along with other substantial bodies like Eris, Makemake, and Haumea. The Kuiper Belt's operations file notes that orbits here are more varied than in the inner system. Some objects follow nearly circular paths close to the ecliptic plane, while others have higher inclinations and eccentricities. Pluto's orbit, for instance, has an eccentricity of about 0.25 and an inclination of 17 degrees, causing it to cross inside Neptune's orbit at times, though the two never collide due to a resonance relationship. Pluto orbits the Sun twice for every 3 orbits of Neptune, a 2 to 3 resonance that keeps their closest approaches separated in time and space. This resonance is logged as a stabilizing factor, allowing Pluto to persist in its current orbit for billions of years. Beyond the Kuiper Belt lies an even more distant region called the scattered disk, where objects have been flung onto highly elliptical and inclined orbits, likely through past interactions with Neptune. These bodies can have perihelia, closest approaches to the Sun, within the Kuiper Belt, but aphelia, farthest distances, stretching far beyond, sometimes hundreds of astronomical units out. The manual describes the scattered disk as an extended storage annex, less organized than the Kuiper Belt, with objects on a wide range of trajectories. Some may eventually escape the solar system entirely, nudged by passing stars or galactic tides over immense timescales. Farther still, the manual includes a speculative section on the Oort cloud, a hypothetical spherical shell of icy bodies surrounding the solar system at distances ranging from thousands to tens of thousands of astronomical units. While no Oort cloud objects have been directly observed in situ, their existence is inferred from the orbits of long-period comets that plunge into the inner solar system from seemingly random directions. The operations file treats the Oort cloud as the outermost inventory zone, a diffuse boundary marking the edge of the Sun's gravitational influence. Objects there orbit so slowly and at such great distances that their periods stretch into millions of years, and they are barely bound to the solar system at all. Comets themselves get their own entry under periodic and one-time visitors. These small icy bodies, typically a few kilometers across, travel on highly elliptical orbits that bring them from the cold outer regions into the inner solar system, where the Sun's heat vaporizes some of their ice, creating bright tails of gas and dust. The manual lists comets by their orbital periods. Short-period comets, like Halley's Comet, return every few decades to centuries, their orbits having been altered by gravitational encounters with the giant planets. Halley's period is about 76 years, meaning it completes a long, stretched loop from beyond Neptune's orbit down past Earth and back out again, returning on a predictable schedule. Long-period comets have orbits measured in thousands or millions of years, often making just one pass through the inner system in all of human history. These visitors are logged as single-entry appointments. A comet appears, brightens as it nears the Sun, then fades as it recedes, not to be seen again for eons. The operations manual treats these rare passages without fanfare. From a scheduling perspective, a comet is simply another object following the gravitational rules, its dramatic appearance from our point of view merely a side effect of its trajectory and composition. The binder notes expected return dates for known short-period comets and lists long-period comets as one-time or extended interval visitors, next return date uncertain. Jupiter's role in shaping small body populations extends beyond the asteroid belt and Trojan swarms. The giant planet acts as a kind of gravitational human resources department, organizing the system's minor bodies through resonances and perturbations. Its massive size, more than 300 times Earth's mass, means even distant objects feel its influence. Over millions of years, Jupiter can alter the orbits of comets and asteroids, sometimes ejecting them from the solar system entirely, sometimes redirecting them into the inner regions, and sometimes capturing them into stable configurations. The manual includes a section on orbital resonances as organizational principles. Resonances occur throughout the system, wherever one object's orbital period is a simple fraction of another's. The 2 to 3 resonance between Neptune and Pluto is one example. The 3-2 resonance between Neptune and many Kuiper Belt objects called Plutinos is another. Jupiter's 4 large moons, Io, Europa and Ganymede, share a resonance where Io orbits 4 times for every 2 orbits of Europa and every 1 orbit of Ganymede, a 4-to-2-to-1 ratio. This configuration keeps the moon's orbit stable and generates tidal heating in Io, powering its volcanic activity. Resonances can also clear regions of the system. The Kirkwood gaps in the asteroid belt are marked in the manual as locations where resonances with Jupiter make long-term stability unlikely. An asteroid at the 3-to-1 resonance, for instance, receives a repeated gravitational kick from Jupiter every 3rd orbit, gradually increasing its eccentricity until it either collides with a planet or gets ejected. The manual flags these as no-go slots, positions that remain mostly empty because any object wandering into them eventually gets nudged out. In contrast, stable resonances like the Trojan's 1-to-1 resonance with Jupiter or Pluto's 2-to-3 resonance with Neptune are logged as allowed positions where objects can persist indefinitely. The current configuration of the solar system wasn't always exactly as it appears in today's manual. An older section of the binder, labelled Historical Revisions, describes how the giant planets likely migrated inward and outward early in the system's history. Models suggest that the planets didn't form in their present orbits, but instead moved gradually over tens of millions of years as they interacted gravitationally with the disk of gas and small bodies that surrounded the young sun. Jupiter may have migrated inward before moving back outward. Saturn, Uranus, and Neptune probably shifted outward, scattering populations of icy bodies as they went. This planetary migration is logged as a long-ago change event, not an ongoing process. The manual's changelog notes, Giant Planet Orbital Adjustment, completed approximately 4 billion years ago. Asteroid and Kuiper Belt populations reorganized, current configuration stable. The Nice model, one version of this migration scenario, suggests that the giant planet's movements triggered a period of heavy bombardment in the inner solar system, sending comets and asteroids careening toward the inner planets. Evidence for this event is recorded in the heavily cratered surfaces of the Moon and other bodies. Once the migration settled down and the planets reached their current orbits, the system entered a stable phase that has persisted ever since. The manual treats this as ancient history, filed away in a section rarely consulted because it doesn't affect day-to-day operations. Each of the giant planets has its own subsystem manual, cross-referenced in the main binder. Jupiter's file is particularly thick, documenting its 60-something known moons, its faint ring system, and its powerful magnetic field. The 4 largest moons, Io, Europa, Ganymede, and Callisto, each have detailed entries listing their orbits, rotations, and physical characteristics. Io's orbit is logged with notes on its resonance-driven tidal heating and intense volcanic activity. Europa's entry highlights its smooth ice-covered surface and the possibility of a subsurface ocean. Ganymede, the largest moon in the solar system, has its own magnetic field noted. Callisto's ancient cratered surface is recorded as evidence of minimal recent geological activity. Dozens of smaller moons orbit farther out, many of them irregular in shape and likely captured asteroids or remnants of past collisions. Saturn's subsystem file is dominated by entries on its magnificent ring system, composed of countless particles ranging from dust grains to house-sized chunks of ice, all orbiting in a thin plane around the planet. The manual describes the rings as maintained by a combination of collisions, which grind larger pieces into smaller ones, and gravitational shepherding by small moons that orbit within and near the rings, keeping the particles confined to narrow bands. The rings' divisions, gaps where particle density drops, are explained by resonances with Saturn's moons. The Cassini division, the most prominent gap, is maintained by a resonance with the moon Mimas. Saturn's moons themselves are numerous, with Titan being the standout, larger than Mercury, with a thick nitrogen atmosphere and lakes of liquid methane on its surface. Titan's entry includes detailed notes on its climate, seasons, and potential for prebiotic chemistry. Uranus and Neptune have their own subsystem files, though less extensive than Jupiter's or Saturn's. Uranus is noted for its extreme axial tilt of about 98 degrees, meaning it essentially rolls along its orbit with its poles alternately facing the Sun. This unusual orientation is logged as stable, likely the result of a massive collision early in the planet's history. Neptune's entry highlights its dynamic atmosphere with the fastest winds in the solar system, and its large moon Triton, which orbits retrograde opposite the direction of Neptune's rotation and is slowly spiralling inward due to tidal forces, though it won't collide with Neptune for hundreds of millions of years. To assess the long-term reliability of the system, astronomers use numerical simulations. They input the current masses, positions and velocities of all the planets into a computer model and let the equations of motion predict future paths. The operations manual includes a stability report based on these simulations. Configuration stable over billions of years. Small oscillations in eccentricity and inclination observed, but no major reordering expected on timescales relevant to human planning. Planetary collisions or ejections assessed as extremely unlikely before the Sun's main sequence lifetime ends. This is the closest the manual comes to a warranty statement. The system isn't perfectly static. Small variations occur, but it won't fall apart or rearrange itself in any dramatic way over the next few billion years. The stability checks reveal that chaotic behavior, while present, operates on very long timescales and within narrow bounds. Mercury's orbit, for instance, shows slight chaotic variations that could, in principle, lead to a significant increase in eccentricity over billions of years, but the probability of Mercury colliding with Venus or being ejected from the system remains low. The manual logs this as an acceptable risk. Minor orbital chaos detected. Outcomes remain within safe operating parameters over the Sun's expected lifetime. For the outer planets, stability is even more robust. Their large masses and wide separations mean they interact only weakly, and their orbits remain predictable for billions of years into the future. While the solar system operates largely as a closed system on human timescales, it is not truly isolated. The manual includes a section on external influences, starting with the fact that the system orbits the center of the Milky Way galaxy once every 225 million years or so. This galactic orbit carries the solar system through different regions of the galaxy, exposing it to varying densities of gas, dust, and stars. Occasionally, stars pass relatively close, within a light year or two, and their gravity can perturb the orbits of objects in the distant Oort cloud, potentially sending some comets plunging toward the inner system. The operations file treats these external events as rare perturbations with minimal impact on the main planetary region. A passing star might alter the orbits of a few distant comets, but the planets themselves, bound tightly to the Sun by strong gravity, remain unaffected. Molecular clouds, large regions of dense gas and dust in the galaxy, can also interact with the solar system, compressing the Oort cloud and triggering a modest increase in comet activity. But again, the inner system's schedule remains unchanged. The manual's external environment section concludes, external perturbations possible on timescales of millions to tens of millions of years, main planetary orbits unaffected over the Sun's expected operational lifetime. One planet in the system has a special annotation, Earth. Its entry in the manual includes a short section on habitability, marked as an unusual but significant feature. Earth's orbit places it within the so-called habitable zone, a range of distances from the Sun where temperatures allow liquid water to exist on a planet's surface. Too close, and water evaporates. Too far, and it freezes solid. Earth's average distance of 1 astronomical unit puts it comfortably in this zone, with surface temperatures moderated by its atmosphere and oceans. The manual notes Earth's axial tilt of about 23.5 degrees, which produces seasonal variations as different hemispheres tilt toward or away from the Sun over the course of the year. Earth's rotation rate, about 24 hours, is logged as contributing to a stable climate. This day length allows heat to redistribute around the planet without extreme temperature swings between day and night. Earth's mass is recorded as sufficient to retain an atmosphere over billions of years, and its magnetic field, generated by a liquid iron core, is noted for deflecting the solar wind and protecting the atmosphere from erosion. The entry includes checkboxes: stable insulation, moderate temperature range, liquid water present, protective magnetic field, suitable atmospheric composition. These conditions have allowed life to develop and persist on Earth, though the manual treats this as one line item among many, a consequence of the planet's physical and orbital parameters, rather than the focus of the entire system's operation. Human observers have filled out much of the solar system manual, through centuries of patient observation. Early astronomers used telescopes to measure planetary positions and calculate orbits, adding the first entries for orbital periods and distances. In the 20th century, spacecraft began flying to other worlds, returning data that filled in details about surface conditions, atmospheric compositions, and magnetic fields. Probes have landed on Mars, Venus, and Titan. Orbiters have mapped Mercury, Jupiter, Saturn, and many moons. Flybys have photographed Uranus, Neptune, Pluto, and numerous asteroids and comets. Each mission appends new pages to the binder, refining existing entries and adding subsections on geology, chemistry, and dynamics. The process is one of steady archival work. A new probe measures the thickness of Europa's ice shell, and a note is added to Europa's file. A telescope detects another dozen Kuiper Belt objects, and their orbits are logged in the inventory. A lander analyzes Martian soil and finds mineral evidence of past water, and the Mars section gets an update on its climate history. The manual grows thicker with each discovery, but the core structure remains the same: masses, orbits, rotations, and compositions, all organized under the unifying policy of gravity and motion. Occasionally, a discovery prompts a revision, Pluto's reclassification from planet to dwarf planet, for example. But these changes are tweaks to the filing system, not overhauls of the fundamental operating principles. Looking far into the future, the manual includes a long-term decommissioning plan. The Sun will not last forever. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core, causing the outer layers to expand. The operations file logs this as the red giant phase. As the Sun swells, it will engulf Mercury and Venus, and possibly Earth as well, depending on details of mass loss and orbital adjustments. Mars and the outer planets will experience increased radiation and heating, but they will remain in orbit, albeit under different conditions. The Sun's mass loss during this phase will cause planetary orbits to expand slightly as the gravitational hold weakens. Eventually, the Sun will shed its outer layers, forming a planetary nebula, and leave behind a dense core called a white dwarf. The white dwarf will cool slowly over billions of years, providing little heat or light. The remaining planets will orbit a faint, dim ember, their surfaces cold and inactive. This entire sequence is documented in the manual's final section, marked Expected System Life Cycle Conclusion. The pages are clean and sparsely filled because these events lie so far in the future that they have no bearing on current or near-term operations. Still, they are part of the system's full documentation, a reminder that even the most reliable office eventually closes down. Returning to the present, the Solar System Manual reveals itself as a neighbourhood that mostly runs itself. The Sun provides a steady energy budget, gravity enforces the rules of motion, planets follow their appointed schedules, orbiting and rotating with metronomic regularity. Moons trace their paths around their parent planets, asteroids fill their designated inventory zones, and comets make their long journeys according to the trajectories set billions of years ago. Humans have learned to read the manual, adding observations and cross-references, but they haven't had to write the rules or enforce the schedules. The system came with those built in, and as long as the Sun keeps shining and gravity keeps pulling, the appointments will continue to be kept. On human timescales, the solar system is remarkably stable. The Earth completes its orbit every year, the Moon circles Earth every month, and the planets line up in configurations that repeat over decades and centuries. These rhythms shape our experience of time, our calendars, and our sense of cosmic order. We can predict eclipses, planetary transits, and comet returns with precision, consulting the manual's tables and trusting that the gravitational rules will not be suspended. The system's predictability is almost mundane, the way a well-run office is mundane. Everything happens on schedule, nothing breaks down, and the daily operations proceed without drama. There are small deviations, of course. Tidal forces gradually slow Earth's rotation, lengthening the day by a tiny fraction of a second per century. The Moon drifts away from Earth at a few centimeters per year as it steals rotational energy from our planet. Asteroid impacts, though rare, do occur, adding chaotic notes to the otherwise orderly record. The manual includes entries for these slow changes and occasional disruptions, but they don't threaten the overall stability. A day lengthening by seconds over millennia, a moon receding at crawling speed, an asteroid hitting every few million years. These are logged as expected variations, not emergencies. The Solar System's Operations Manual doesn't have chapters on heroism or adventure. It doesn't describe battles between worlds or the intervention of cosmic overseers. Instead, it documents a system that was set in motion long ago and has been coasting ever since, governed by simple universal rules that require no ongoing supervision. The drama, if any, happened in the early days, during planet formation, migration, and the heavy bombardment, and those events are filed in the historical section, not in current operations. Today's manual is a collection of steady states, equilibrium configurations, and repeating cycles, all described with the calm precision of engineering documentation. If you were to close the binder and place it back on its shelf, you might feel a certain quiet satisfaction. The solar system is not a place of constant upheaval or impending disaster. It's a place where things work, where the rules are simple and consistent, and where the schedule is kept with astonishing fidelity. Mercury will return in 88 days, Jupiter in 12 years, Neptune in a century and a half. The Sun will rise tomorrow as it did today, and, as it has for billions of days before. The manual doesn't promise excitement, but it does promise reliability, and in the vastness of space, reliability is perhaps the greatest comfort of all. As you drift towards sleep, imagine that thick manual resting on its cosmic bookshelf, its pages filled with numbers and diagrams, its tabs marking the sections for each planet and moon. Picture the latest entry being added. Today's date, another lap completed, another rotation logged. The office is still running smoothly. The sun is still shining at its appointed luminosity. The planets are still keeping their appointments. And somewhere among all those orbits and rotations, our small blue world is quietly attending its regular shift, spinning once per day, circling the sun once per year, hosting life and thought and the work of filling out the manual, one observation at a time. The neighbourhood, as always, is in good order. The next story is about to begin. Please relax and enjoy. Tonight we're not turning the moon into a symbol or a myth. We're opening Earth's long-term maintenance manual and flipping to the lunar satellite section. The moon is treated like a quiet, dependable co-worker whose job is to orbit, tug on the oceans, and keep time. Imagine its behaviour recorded in neat lines: orbital period, average distance, tidal effects, and a note about how many millimetres farther away it is this year compared to the last. No drama, just scheduled tasks and log entries. The leading idea for how the moon formed goes like this. About 4.5 billion years ago, a Mars-sized body collided with the early Earth. The impact was enormous, ejecting a massive amount of debris into orbit around our planet. Over time, this debris, molten fragments, dust and vaporized rock, clumped together under its own gravity to form a single large satellite. In the maintenance log, this is the original installation entry. System event, major impact, debris ring formed, satellite accreted from molten fragments. The details go into a quiet table. Composition similar to Earth's outer layers, mostly silicates and metal. Initial orbit closer in, much closer than today. Rotation and tilt still settling. It's not a legend, just a messy early entry in the file that sets the initial parameters. The moon didn't arrive gently. It was born from violence and chaos, but that's just how the system got started. After that, the clock began ticking. The early moon would have been hot, incredibly hot. Imagine a globe of molten rock, glowing red and orange against the black of space. A global magma ocean covered the entire surface, slowly cooling over millions of years. As it cooled, the physics were straightforward. Lighter minerals floated upward to form a primitive crust, while heavier materials sank deeper toward the core. This entire process is a long thermal adjustment noted in the log. Surface temperature decreasing, crust forming. Large-scale lava seas later filling basins. No fanfare, just a sequence of cooling milestones, each with estimated times and temperatures. The moon's first solid surface wasn't dramatic, it was inevitable. Heat radiated into space, convection currents stirred the molten interior, and gradually over tens of millions of years, a stable outer shell formed. That shell was lighter in colour, made of anorthosite and other low-density minerals. Beneath it, denser materials settled into what would become the mantle. The moon was becoming a structured body, layered and cooling, logging thermal data point by thermal data point. The Moon's initial orbit after formation was likely closer to Earth and possibly more eccentric, meaning less circular. The debris ring that formed the Moon was chaotic, and the early orbital path reflected that chaos. But over time, gravitational interactions and tidal effects smoothed things out. The Moon and Earth tugged on each other, exchanging energy and momentum. The orbit circularized, becoming rounder and more predictable. In the service manual, engineers would mark this as orbit damping, eccentricity decreasing, inclination adjusting, orbital period lengthening. The Moon's path became regular enough to predict far into the future, turning from a leftover debris cloud into a reliable satellite with a clean orbital line. This wasn't instantaneous. It took millions of years for the orbit to settle into something stable. But once it did, the Moon had found its groove, a repetitive ellipse that it would trace over and over again, with only the slowest of drifts to mark the passage of deep time. Tidal locking came next, and it's worth explaining in simple, mechanical terms. Earth's gravity doesn't just pull on the Moon as a point mass, it raises small bulges in the Moon's body. Early on, the Moon rotated faster than it orbited. As it spun, these bulges lagged slightly behind the Earth-Moon line, always trying to point toward Earth but falling a bit behind due to the Moon's rotation. This lag created tiny torques, friction-like forces that acted as a brake on the Moon's spin. Over millions of years, these torques gradually slowed the Moon's rotation until it matched its orbital period. Now the Moon spins once per orbit, so the same hemisphere always faces Earth. In the maintenance log, this is recorded as rotation rate adjusted to match orbital period, state, spin orbit synchronized. From that line onward, the near side and far side became permanent roles. The near side, the face we see, is locked toward Earth. The far side, often incorrectly called the dark side, faces away. Both sides get sunlight during the lunar day, but only one side ever sees Earth. It's a stable configuration, the result of billions of years of gravitational massage. Now turn to Earth's side of the interaction. The Moon's gravity pulls a slight bulge in Earth's oceans toward it, and because Earth rotates faster than the Moon orbits, this bulge leads the Moon a little. There's also a matching bulge on the opposite side caused by inertia and the way gravitational gradients work across Earth's diameter. As Earth spins, different regions pass under these bulges, experiencing high and low tides. In the log, each coastal region has a simple recurring entry: 2 high tides and 2 low tides per lunar day, local variations noted. The lunar day, the time it takes for the Moon to return to the same position relative to a point on Earth's surface, is about 24 hours and 50 minutes, so high tides come roughly twice a day, shifting later each day by about 50 minutes. It's a repetitive but crucial item in Earth's daily checklist. Tides mix the oceans, stir nutrients, shape coastlines, and power ecosystems in the intertidal zones. The Moon doesn't care about any of this, but the log notes the effects dutifully. The tidal bulges don't just raise and fall, they also tug on the Moon. Because Earth rotates faster than the Moon orbits, the tidal bulge is dragged ahead of the Moon. This bulge has mass, and its gravity pulls the Moon forward in its orbit, transferring a bit of Earth's rotational energy to the lunar orbit. The result is twofold. Earth's rotation slows slightly, and the Moon's orbit slowly spirals outward. Days get longer by about 1.7 milliseconds per century, a change so small that you'd never notice it in a lifetime, but significant over geological timescales. The Moon, meanwhile, drifts away at about 3 to 4 centimeters per year. In the maintenance file, there's a long, slow table. Earth day length, increasing. Mean Earth-Moon distance, increasing approximately 3 to 4 centimeters per year. It's like a very slow, ongoing adjustment note in the system. This process has been happening since the Moon formed. Early on, when the Moon was much closer, the tidal forces were stronger and the rate of change was faster. Days were shorter, perhaps only a few hours long billions of years ago. The Moon loomed larger in the sky. Over time, everything has been winding down, slowing, drifting, settling into the current configuration. The Moon's presence helps stabilize Earth's axial tilt, the angle between our rotation axis and our orbit around the Sun. Currently, Earth's tilt is about 23.5 degrees, and it wobbles slightly over tens of thousands of years, but only within a narrow range. This is largely thanks to the Moon. The Moon's gravitational pull on Earth's equatorial bulge provides a stabilizing torque. Without this, computer models suggest Earth's tilt might wobble much more chaotically over long timescales, swinging through a wider range of angles. Such wobbles could lead to more extreme climate swings, with the poles pointing more directly toward or away from the Sun at different times. In the climate appendix of the manual, the Moon's entry reads, "Provides stabilizing torque on spin axis, reduces chaotic variations in obliquity." This doesn't mean perfect stability. Earth's tilt does change, and ice ages come and go, but the Moon keeps those changes more gradual and predictable. This is helpful for long-term climate patterns and the conditions for life. It's not that life couldn't exist without the Moon, but the Moon makes Earth's climate a bit more stable, a bit more forgiving. The Moon's surface is a physical incident log, with no atmosphere, no rain, no wind to speak of, and no plate tectonics to erase marks. Impacts stay preserved for billions of years. Each crater is like a stamped date, even if we don't know the exact time without further analysis. Small craters from micrometeoroids pepper the surface. Massive basins from large asteroids dominate entire regions. In the manual, this is an unrolling list. Impact events recorded on surface, large basins filled by later lava flows, regolith, a dust layer gradually built up. The surface is less a dramatic battlefield and more a dusty archive. Every piece of rock that has struck the Moon has left its mark, from boulders to grains of sand. Over time, these impacts have ground the surface rock into a fine powder, the regolith, which covers the Moon to depths of several meters in many places. The larger impacts fractured the crust, allowing molten rock from the interior to well up and flood low-lying areas. This process created the Maria, the dark plains we see from Earth. There are two main types of lunar terrain, and they're easy to describe in plain terms. The lighter, heavily cratered highlands are older crust, the original surface that formed as the magma ocean cooled. The darker, smoother Maria are ancient lava plains formed when large impacts fractured the crust and allowed molten rock to flood low areas. In the log, a simple terrain classification table lists highlands, older, lighter coloured, more craters, and Maria, younger, basaltic plains, fewer superposed craters. It's just a geology file. Two main surface kinds, their ages and their compositions. The highlands are anorthosite-rich, light and ancient, dating back over 4 billion years. The Maria are basaltic, dark and denser, mostly between 3 and 4 billion years old. The Maria formed after the period of heavy bombardment began to taper off, filling in the giant impact basins that had been carved earlier. From Earth, the Maria form the familiar patterns we see. The man in the moon, or other shapes depending on your culture and imagination. But in the manual, they're just labelled regions. Mare Tranquillitatis, Mare Serenitatis, Oceanus Procelarum. Each with notes on composition, estimated age and thickness of the lava flows. Lunar phases are nothing more than changing angles between the Sun, Earth and Moon. As the Moon orbits Earth, we see different fractions of its sunlit half. At new moon, the Moon is between Earth and the Sun, and its sunlit side faces away from us. We see darkness. As the Moon moves in its orbit, we begin to see a sliver of light, a crescent. At first quarter, we see half the Moon's disk illuminated. The Moon continues around, waxing to gibbous, then to full moon, when Earth is between the Sun and the Moon, and we see the entire sunlit hemisphere. Then the cycle reverses, waning gibbous last quarter, waning crescent, back to new. In the maintenance manual, this appears as a repeating cycle schedule. Synodic month approximately 29.5 days. Phase angle increases smoothly from 0 degrees, new moon, to 180 degrees, full moon, and back. Phases that once inspired myths are here reduced to a circular geometry diagram and a calendar table of predictable dates. The Moon doesn't change, our view of it does. The geometry is simple and elegant, a consequence of orbits and sunlight. Nothing mystical about it. Solar and lunar eclipses are special, but entirely geometrical, entries in the log. A lunar eclipse occurs when Earth's shadow falls on the Moon. This can only happen at full moon, when the Sun, Earth, and Moon are roughly aligned with Earth in the middle. The Moon passes through Earth's shadow, often turning a coppery red due to sunlight refracted through Earth's atmosphere. A solar eclipse occurs when the Moon's shadow passes over parts of Earth. This can only happen at new moon, when the moon is between Earth and the Sun. Because the moon's orbit is slightly tilted relative to Earth's orbit around the Sun, about 5 degrees, these alignments only happen sometimes. There are specific times, called eclipse seasons, when the geometry is just right. The manual lists eclipses as alignment events, predicted using orbital nodes, distances, and timing formulas. No omens, just extra pages in the schedule with precise times and paths, calculated long in advance. Eclipse predictions are some of the oldest successful scientific predictions, going back thousands of years. Ancient astronomers noticed the patterns and worked out the cycles. The Saros cycle, for example, is about 18 years and 11 days, after which eclipses repeat in a similar pattern. All of this is recorded in the log, neat tables of past and future eclipses, with paths drawn on maps of Earth. Libration is a small apparent rocking motion that lets us see a bit more than 50% of the lunar surface over time. Even though the moon is tidally locked, its orbit isn't perfectly circular, and the moon's rotation rate is constant while its orbital speed varies slightly. When the moon is closer to Earth in its orbit, it moves faster. When farther, slower. But its rotation rate doesn't change. This means we sometimes see a bit more of the eastern or western edge. Additionally, the moon's orbit is tilted slightly relative to Earth's equator, so we sometimes see a bit more of the northern or southern edge. Combined, these effects, called librations, allow us to see about 59% of the moon's surface from Earth over time. In the log, libration is a minor note. Apparent disk shifts slightly, limb features alternately exposed and hidden. Another small periodic entry in the moon's behaviour record. It's a small wobble, a slight sway, nothing dramatic but enough to give us glimpses of regions that would otherwise be hidden. Many human cultures have used the moon as a natural clock. The lunar cycle is obvious and regular, easy to observe without instruments. Months were originally tied to the moon's phases. The word month itself derived from moon. Even today, some calendars retain a close relationship between months and the moon's phases. Lunar calendars, like the Islamic calendar, have months that strictly follow the lunar cycle, each beginning with the sighting of the new crescent. Lunisolar calendars, like the Hebrew or Chinese calendars, try to keep months aligned with the moon while also keeping years aligned with the sun, adding leap months as needed. In Earth's administrative appendix, the moon's influence appears as timekeeping reference, synodic month used for months and festivals, eclipse cycles used for long-term prediction. The moon doesn't know it's on our calendars. We simply borrowed its regularity for scheduling. Before mechanical clocks, the moon was one of the best ways to mark time at night, to plan agricultural activities, to schedule religious festivals. The moon's phases were a shared, universal reference that everyone could see. For a brief period in the 20th century, humans added a new type of entry to the log: direct visits. Spacecraft orbited, landed, and returned samples. The Apollo missions between 1969 and 1972 brought 12 astronauts to the moon's surface. Their footprints are still there, preserved in the regolith with no wind or rain to erase them. Instrument packages were left behind, some of which still function. Retroreflectors, arrays of mirrors used to bounce laser beams back to Earth, sit at several Apollo landing sites. Scientists still use them to measure the Earth-Moon distance with centimetre precision, which is how we know the moon is drifting away at about 3.8 centimetres per year. In the manual, these missions appear as temporary operations, experiments left on site to measure moonquakes, reflect laser pulses, and record environmental conditions. Compared to billions of years, they are tiny footnotes, but they gave us higher resolution pages in the moon's data file. The samples returned, over 300 kilograms of moon rocks and soil, allowed scientists to determine the moon's age, composition, and history with far greater accuracy than telescopes alone ever could. We learned about the lunar magma ocean, the age of the Maria, the lack of water in the lunar interior. We confirmed that the moon is not a captured asteroid, not a co-formed twin, but a child of Earth, born from the same material in a giant impact. The moon's story continues far beyond human timescales. As Earth's rotation keeps slowing and the moon keeps drifting away, the length of the day and the apparent size of the moon in our sky will change. The day will get longer, the moon will appear smaller. Currently, the moon's apparent angular size is about half a degree, close enough to the sun's apparent size that total solar eclipses are possible. but as the moon drifts away it will appear smaller, and eventually total solar eclipses will no longer occur. The moon will be too small to completely cover the sun, and only annular eclipses where a ring of sunlight remains visible will happen. In the maintenance log, the far future entries read, mean distance, increasing, apparent angular size, decreasing, eclipse type, gradually shifting from total to annular only. It's all scheduled as slow, predictable changes. In a few 100 million years, total eclipses will be a thing of the past. In a few billion years, the moon will have drifted so far that tidal locking might work the other way. Earth's rotation might slow enough that one side of Earth always faces the moon, just as one side of the moon always faces Earth now. But this is so far in the future that other factors, like the sun's evolution into a red giant, will likely intervene first. The moon's contributions to Earth's broader system are worth tying together. Tidal mixing affects ocean circulation, stirring nutrients from the deep ocean to the surface, which supports marine ecosystems. The moon's gravity helps drive thermohaline circulation, the global conveyor belt of ocean currents that redistributes heat around the planet. The intertidal zones, areas of coastline that are alternately submerged and exposed by tides, are among the most productive ecosystems on Earth, rich in biodiversity and serving as nurseries for many marine species. The moon stabilizes Earth's tilt, which helps keep climate patterns more predictable over long timescales. The regular pattern of lunar phases has been synchronized with by many coastal ecosystems and human cultures, influencing behaviors, migrations, and traditions. These show up in the general Earth system ledger as external forcing term lunar tides, with side notes about their influence on nutrient mixing, intertidal zones, and sediment transport. Nothing mystical, just another steady input variable in the climate and ocean circulation equations. The moon is a quiet partner in Earth's habitability, not essential in an absolute sense, but helpful, stabilizing, and deeply interwoven with the rhythms of life on our planet. The moon's job in the manual is not spectacular. It orbits, stays tidally locked, pulls on the oceans, slowly drifts away, keeps our tilt steadier, and provides a reliable pattern of phases and occasional eclipses. All of this is written as lines of numbers and brief comments in Earth's long-term service file. There are tables of orbital parameters, semi-major axis, eccentricity, inclination, orbital period. There are notes on surface composition, Maria versus Highlands, regolith depth, crater densities. There are tidal force calculations, angular momentum transfer rates, and projections for future orbital evolution. There are schedules of lunar phases, eclipse predictions, and libration cycles. There are historical notes, formation by giant impact, magma ocean cooling, tidal locking achieved human visits in the late 20th century. There are ongoing measurements, laser ranging data, seismic readings from old instruments, observations of transient phenomena like meteor impacts. The file is thick, detailed, and mostly predictable. The moon is a well-understood system, its behavior modelled and projected with high confidence. Imagine a binder labelled Lunar Subsystem, full of charts and tables. Every so often, someone flips through it, checks the latest measurements, updates a few numbers. The moon's performance is reviewed, and always marked, operating nominally. It's a grey, quiet co-worker that has kept its orbital appointment for billions of years and shows no sign of missing the next one. It doesn't need supervision. It doesn't require maintenance beyond the natural processes already at work. It just keeps going. A satellite doing satellite things, predictable and reliable. The romance is there if you want to find it. The same face always watching Earth, the slow drift that will one day end total eclipses, the ancient surface that holds the memory of the solar system's violent youth. But you don't need romance to appreciate the moon. You can just appreciate the fact that it works, that it's there, that it will be there tomorrow night and the night after, rising and setting, waxing and waning, tugging on the oceans, stabilizing the tilt, keeping time. The moon is not a goddess, not a beacon, not a destination in any grand sense beyond the handful of missions we've sent. It's a natural satellite, 184 times smaller than Earth by mass, orbiting at an average distance of 384,000 kilometers. It has no atmosphere to speak of, no magnetic field, no liquid water, no life. Its surface temperature swings from about 100 degrees Celsius in direct sunlight to minus 170 degrees Celsius in shadow. It is airless, waterless, lifeless, and quiet. It is also beautiful in its simplicity, in the way it fits so neatly into the equations, in the way its behaviour can be predicted centuries in advance with nothing more than Newton's laws and a bit of calculus. The moon is evidence that the universe has patterns, that chaos can settle into order, that even violent beginnings can lead to stable, long-lasting systems. It's a reminder that not everything needs to be complex or exotic to be important. Sometimes the most important things are the ones that just keep showing up, doing their job, reliable and steady. The moon doesn't need to do anything more than it does. It doesn't need to surprise us or inspire us, though it often does both. It just needs to be there, orbiting, a constant in a changing world. The maintenance log will keep growing. Future generations will add their own entries. Perhaps more missions will land on the surface, setting up permanent bases, mining resources, or simply studying the moon in greater detail. Perhaps new instruments will measure things we haven't thought to measure yet, refining our understanding of the lunar interior, the distribution of water ice in permanently shadowed craters, or the effects of the solar wind on the regolith. Perhaps the moon will become a waypoint for missions to other parts of the solar system, a convenient place to refuel or resupply. Or perhaps the moon will remain mostly untouched, visited occasionally but left largely alone, a museum of the early solar system, a natural laboratory, a quiet presence in the sky. Whatever happens, the moon will keep orbiting. It will keep raising tides, stabilizing Earth's tilt and drifting slowly away. It will keep cycling through its phases, casting light on Earth's nights and occasionally aligning just right to produce an eclipse. It will keep absorbing impacts, building up its regolith and preserving the scars of its long history. And somewhere, in a file cabinet or a database or a digital archive, the maintenance log will keep recording it all, adding line after line of data, updating the tables, extending the projections. The log is never finished. It's an ongoing record of a system that has been running for 4.5 billion years and will keep running for billions more. You can look up at the moon tonight and see all of this or none of it. You can see a symbol, a myth, a memory, a goal, or you can see a spheroid of rock and metal tidally locked, cratered, drifting slowly away. You can see what you want to see. The moon doesn't mind. It's not performing for you. It's just there, doing its job, logged and accounted for, predictable and reliable. It's the most boring maintenance task in the solar system, and it's been running smoothly for eons. The moon is not here to impress you. It's here to orbit, and it's very good at it. And that's enough. That's always been enough. But let's flip through a few more pages of the manual, because there are details worth noting, small entries that fill out the picture of this reliable satellite. The moon's internal structure, for instance, deserves a subsection. Beneath the crust, which varies from about 30 to 60 kilometers thick on the near side and up to 150 kilometers on the far side, lies the mantle. The mantle is composed of silicate minerals, similar to Earth's mantle but with some important differences. The moon is much drier than Earth, with very little water locked into its minerals. This affects how heat is transported through the interior and how the mantle behaves over geological time. Below the mantle sits a small core, probably made of iron with some nickel and other elements, perhaps 200 to 400 kilometers in radius. This core may be partially molten, but it's small enough that it doesn't generate a significant magnetic field today. The moon once had a magnetic field billions of years ago, recorded in the magnetization of certain rocks returned by the Apollo missions. But that field has long since died away, its dynamo shut down as the moon cooled, and its interior became less active. The moon's lack of a magnetic field has consequences. Without a protective magnetic bubble, the lunar surface is exposed directly to the solar wind, a stream of charged particles flowing outward from the sun. Over time, these particles have altered the very top layer of the regolith, creating what's called space weathering. The regolith darkens, its optical properties change, and tiny beads of iron are formed through micrometeorite impacts that melt and resolidify grains. This process is logged in the surface alteration section of the manual: solar wind exposure, continuous, space weathering effects, ongoing, regolith, maturity, increasing with age. It's a slow transformation, measured in millions of years, But it's one reason why older surfaces on the Moon look darker and redder than younger ones. The regolith itself is an engineering concern for anyone planning to spend time on the Moon. It's not like beach sand or desert dust. Lunar regolith is jagged, sharp-edged and clingy. Without water or wind to round the grains, they remain angular, almost like tiny shards of glass. They stick to everything: spacesuits, equipment, seals. During the Apollo missions, astronauts found that regolith worked its way into joints and mechanisms, abrading surfaces and causing problems. In the manual's Human Operations Appendix, there's a cautionary note. Regolith properties: abrasive, electrostatically charged, fine-grained, mitigation required for long-term surface operations. Future missions will need to account for this, developing better seals, coatings and cleaning procedures to deal with the dust. Temperature management on the Moon is another challenge worth noting in the operations section. With no atmosphere to buffer temperature changes, the surface heats and cools dramatically between day and night. The lunar day, remember, lasts about 29.5 Earth days, so there are roughly 2 weeks of continuous sunlight, followed by 2 weeks of darkness. During the day, surface temperatures in direct sunlight can reach 100 degrees Celsius or more. At night, they plummet to minus 170 degrees Celsius or lower. Any equipment or habitat on the surface needs to handle these swings. The manual notes: thermal environment, extreme diurnal variation, active thermal control required for sustained operations. Astronauts and equipment can't simply rely on passive insulation. They need heaters, radiators, and careful planning to manage heat. There are places on the Moon where the temperature is more stable, deep craters near the poles. Some of these craters are in permanent shadow, never receiving direct sunlight. In these dark, cold traps, temperatures remain extremely low year-round, cold enough that water ice can persist for billions of years. Recent missions have confirmed the presence of water ice in these permanently shadowed regions. The manual's resource appendix lists this as water ice deposits, present in polar cold traps, quantity, estimated in millions of metric tons, accessibility, moderate to difficult depending on location. This ice is valuable, not just scientifically but practically. Water can be split into hydrogen and oxygen, providing rocket fuel and breathable air. It can be used for drinking and agriculture. The presence of water ice on the Moon changes the calculus for future exploration and settlement. It's a resource that doesn't need to be brought from Earth, reducing the cost and complexity of long-term lunar operations. The Moon also experiences moonquakes, though they're different from earthquakes. There are several types. Deep moonquakes occur about 700 kilometers below the surface and are thought to be caused by tidal stresses from Earth's gravity. Shallow moonquakes are rarer but can be more energetic, possibly caused by thermal expansion and contraction of the crust or by stress release in faults. Meteorite impacts also generate seismic waves, and there are even thermal moonquakes caused by the rapid heating of the surface at sunrise. The Apollo seismometers recorded thousands of these events, and the data is still being analysed. In the seismic activity section of the manual, there's a table: deep moonquakes, regular tidal correlation, shallow moonquakes, infrequent, higher magnitude, impact events, sporadic, thermal quakes, diurnal pattern. The Moon is not seismically dead, but it's far quieter than Earth. There's no plate tectonics, no volcanic activity today, just the subtle creaks and groans of a cooling, tidally stressed body. Volcanic activity on the Moon is a thing of the past. The Maria were formed by ancient lava flows, but those flows ceased billions of years ago. The Moon's interior has cooled enough that large-scale melting no longer occurs. There might be tiny pockets of melt deep down, but nothing that reaches the surface. The manual's volcanic history section notes: last major eruptions, approximately 3 billion years ago. Current volcanic activity, none. Magma source regions, depleted and cooled. This makes the Moon fundamentally different from Earth, where volcanism is ongoing and vital to the planet's geology and atmosphere. The Moon's geology is frozen in time, a snapshot of processes that happened early in its history. The Moon's gravity is about 1/6 of that of Earth's, which has implications for everything from walking to orbital mechanics. Astronauts on the Moon could jump higher, carry more weight, and move in ways that would be impossible on Earth. But lower gravity also means a lower escape velocity, only about 2.4 kilometers per second compared to Earth's 11.2. This makes the Moon an attractive place to launch missions to other parts of the solar system. Fuel requirements are much lower, and there's no atmosphere to fight through. The manual's orbital mechanics section includes a note: escape velocity, low, delta V requirements for departure, favourable, potential use as launch platform, under consideration. The Moon could serve as a staging area for missions to Mars, the asteroid belt or beyond, a stepping stone that makes the solar system more accessible. The Moon's orbit isn't static, it's influenced by more than just Earth. The Sun's gravity perturbs the Moon's orbit, causing small variations in its path. These perturbations are predictable and well modelled, but they add complexity to the orbital calculations. There are also resonances and interactions with other aspects of Earth's motion, like the precession of the equinoxes. The manual's orbital perturbation section lists these factors: solar perturbations, present, primary third body effect, planetary perturbations, minor, Earth's oblateness, causes lunar apse precession. All of these effects are small, but over long timescales they matter. Accurately predicting the Moon's position months or years in advance requires accounting for all of them. The Moon's role in shaping human culture extends far beyond timekeeping. Lunar cycles have been linked to biological rhythms in many species, from coral spawning to the behaviour of certain insects and fish. While the evidence for direct lunar effects on human biology is mixed and often overstated, there's no denying that the Moon has shaped human culture, art, and imagination. Countless stories, poems, songs, and paintings have been inspired by the Moon. It has been a symbol of femininity, mystery, change, and constancy, depending on the culture and context. In the manual's cultural influence appendix, there's a simple acknowledgement: cultural significance, extensive across human societies, symbolic associations, variable, practical uses in navigation and timekeeping, historical and ongoing. The Moon doesn't create these meanings, but humans have projected them onto it for as long as we've been looking up. Navigators have used the Moon for centuries. Before GPS and radio, sailors used the Moon's position relative to stars to determine longitude. Lunar distances, the angular separation between the Moon and certain stars, could be measured and compared to tables to figure out time and position. This method was tedious and required precise instruments and calculations, but it worked. The manual's navigation appendix notes: use in celestial navigation, historical method, lunar distance calculations, current relevance, minimal due to electronic systems, legacy, significant in maritime history. The Moon was a tool, a reference point in the sky, helping people find their way across featureless oceans. The Moon's influence on language is also worth a footnote. Words related to the Moon appear in many languages, often with connections to time, cycles, and change. Lunacy, the old belief that the full moon could drive people mad, comes from luna, the Latin name for the moon. Monday, the day of the week, is Moon Day in many Germanic languages. Menstruation and month both derive from roots related to the Moon and its cycle. These linguistic traces are logged in the cultural appendix. Etymological influence, present in multiple language families, terms related to time, cycles, and mental states, persistence in modern language, ongoing. The Moon has worked its way into how we talk and think, a background presence in the structure of language itself. There are mysteries still surrounding the Moon, gaps in the maintenance log that future observations might fill. The exact composition and state of the Moon's core remain uncertain. We don't know for sure whether it's solid or partially liquid, or precisely what mix of elements it contains. The distribution of materials in the lunar interior is still being refined through techniques like seismic analysis and gravitational measurements from orbiting spacecraft. The manual's unresolved questions section lists these: core composition, iron-rich, exact state uncertain, deep interior structure, models improving, gravitational anomalies, mascons, understood in general, details ongoing. Even a well-studied body like the Moon has unknowns, places where the log has entries marked data pending, or requires further investigation. Mascons, short for mass concentrations, are regions of higher density beneath some of the Maria. They were discovered when spacecraft orbiting the Moon experienced slight accelerations as they passed over these areas, indicating stronger gravitational pull. Mascons are thought to be dense basaltic lava that filled the impact basins, combined with possible uplifted mantle material. They're noted in the gravitational anomalies section, mascons, present beneath major impact basins, gravitational signature, positive anomaly, implications for interior structure and basin formation, significant. These features affect orbital mechanics slightly, requiring corrections for spacecraft orbiting close to the Moon. The Moon has also been proposed as a site for telescopes, both optical and radio. The far side of the Moon is one of the most radio-quiet places in the solar system. The next story is about to begin. Please relax and enjoy. Tonight we're going to open a very particular kind of file. Imagine it as an enormous spreadsheet, the sort that might take up an entire wall if printed, with columns stretching back through decades and centuries. This is the Global Incident Log, a hypothetical but useful document where every act of violence, every conflict, every harm done by one person to another gets recorded with the same dry precision you'd find in an accountant's ledger. There are columns for homicides, subdivided by region and year. There are columns for wars, with casualty counts and dates. There are sections for traffic deaths, workplace accidents, domestic violence reports, assaults logged by police departments, and 1,000 other categories of harm that human beings inflict on each other, intentionally or otherwise. The numbers go back as far as records allow, patchy and incomplete in some centuries, meticulously detailed in others. What we're doing tonight is not reliving frightening news clips or dwelling on the worst of humanity. Instead, we're simply going to look at this log, compare what we feel about violence to what the long-term records actually show, and ask a gentle technical question. Does the world truly get more violent over time, or has our experience of violence changed faster than the underlying numbers? Before we can make sense of any spreadsheet, we need to understand what we're counting. Violence is a broad word, almost uselessly broad if we're trying to be precise. Does it include only intentional harm? What about reckless behaviour that kills? What about structural harms, the slow grinding poverty that shortens lives? For our purposes tonight, we'll define our categories carefully and keep them measurable. The global log includes intentional killings, what criminologists call homicides, because these are the most consistently recorded across different societies and time periods. It includes deaths and injuries in armed conflicts, whether between nations or within them, because wars and civil conflicts leave trails in military records, hospital tallies, and historical accounts. It includes reports of domestic violence, sexual assault, child abuse, and other interpersonal harms, though these categories become clearer and more complete only in recent decades as reporting systems developed. And it includes some forms of accidental harm, traffic fatalities, industrial accidents, deaths from unsafe working conditions, because these shape our overall sense of whether the world is a dangerous place to move through. Each category gets its own column, with counts, rates per 100,000 people, and timestamps. The tone here is pure bookkeeping. We're not dramatising, we're organising. To understand the present entries in this log, we need to glance back at the historical pages, where the ink is faded and many rows are missing entirely. Before modern states with their police forces, hospitals and statistical bureaus, violence was harder to measure but often woven more tightly into the fabric of daily life. In medieval Europe, for instance, local feuds could erupt into killings that went unpunished or were settled through compensation rather than prosecution. Raids between neighbouring communities were common in many parts of the world. Corporal punishment was a standard feature of justice systems and household discipline. There was no 911 to call, no emergency room down the street, no formal system to track and respond to harm. Many violent events simply never made it into any written record. A fight in a village, a death during childbirth complicated by assault, a traveller robbed and killed on a lonely road. In our metaphor, the early pages of the incident log are scattered and incomplete, full of gaps where we have to make educated guesses based on court records, tax rolls, coroner's inquests, and the occasional chronicle written by a monk or court official. But the fragments we do have often hint at rates of lethal violence that were significantly higher than what we see today in many regions, especially during periods of political instability or weak central authority. As we move forward through the centuries in our logbook, one column becomes clearer and more reliable than almost any other: homicide rates. Intentional killings are relatively likely to be recorded wherever there are courts to try accused murderers, hospitals and physicians to certify causes of death, and police or similar authorities to investigate suspicious deaths. This makes homicide data one of our best long-term indicators of violent crime. Countries around the world now track homicides per 100,000 people per year. a standardized measure that allows us to compare violence levels across regions and decades. In the incident log, this becomes one of the tidiest columns, lines on a graph going up or down over time, with marginal notes about policy changes, economic shifts, demographic patterns, and cultural transformations. When we look at this column carefully, region by region, we see some striking patterns. Many Western European countries, for instance, had homicide rates in medieval times that scholars estimate at 20, 30, even 50 per 100,000 in some cities and periods, numbers that would be considered catastrophic today. Over the centuries, these rates gradually declined. By the 19th century, they had fallen to single digits in many places. By the late 20th century, countries like Germany, France, and the United Kingdom were recording homicide rates well below 2 per 100,000. The United States shows a more complex pattern, rates that peaked in the early 1990s and then fell substantially over the following 2 decades, though they remain higher than most other wealthy nations. Latin America shows a different story, with some countries experiencing very high homicide rates in recent decades, driven by organised crime, gang violence, and weak state capacity. Sub-Saharan Africa has uneven data, but where records are available, rates vary widely by country and period. The point is not that violence has disappeared, or that every place follows the same trajectory, but that when we look at this particular column over long stretches of time, the trend in many regions is not upward, but downward, or fluctuating within ranges that would have seemed remarkably safe to people living centuries ago. Another major section of the log covers organised violence, wars, civil conflicts, armed clashes between groups. Here the record-keeping changes dramatically over time. In ancient and medieval periods, we have estimates of battlefield casualties from major wars, often based on historical accounts that may exaggerate or minimise numbers depending on who was writing. The Napoleonic Wars, the 30 Years' War, the Mongol conquests, each produced enormous death tolls, though exact figures remain uncertain. In the 20th century, the 2 world wars dominate the conflict column with their staggering casualty counts. Tens of millions of military and civilian deaths in World War I, even more in World War II when civilian targeting and industrial-scale killing reached unprecedented levels. These spikes in the log are massive, towering over almost everything that came before in their absolute numbers, though as a percentage of global population the picture becomes more nuanced. Since 1945, something remarkable appears in the data: the absence of another world war and a general decline in battle deaths from interstate conflicts. This doesn't mean war disappeared. Civil wars, insurgencies, and regional conflicts have continued to kill and displace millions, but the pattern of massive state versus state warfare that characterized the first half of the 20th century has not repeated itself at the same scale. Research groups like the Uppsala Conflict Data Programme and the Peace Research Institute Oslo now maintain detailed databases of armed conflicts, tracking deaths year by year, categorizing conflicts by type, recording ceasefires and escalations. In our incident log, war deaths still appear as spikes, some large ones in places like Syria, Yemen, and the Democratic Republic of Congo in recent years, but these are set against long stretches of relative peace for most of the world's population. The deadliest single day of World War II, in terms of civilian deaths, might have seen more people killed than in entire years of current global conflict. This is not to minimise the horror of ongoing wars, but to place them in their historical context within the log. The log also needs columns for everyday risks that shape our sense of whether life is dangerous: traffic accidents, workplace injuries, deaths from unsafe conditions. Historically, many of these harms were far more common before modern safety systems existed. In the early days of industrialization, factory work was extraordinarily dangerous. Workers lost limbs to machinery, miners died in collapsed shafts and gas explosions. Children laboured in conditions that routinely injured or killed them. There were no hard hats, no safety inspections, no workers' compensation systems. As public health movements, labour organising and government regulation developed, these risks began to decline in many countries. Traffic deaths tell a similar story in some places. As cars became common in the 20th century, road fatalities surged, but then the introduction of seat belts, speed limits, drunk driving laws, airbags, and better road design brought rates down in many wealthy countries even as the number of vehicles continued to grow. In the spreadsheet, These accident columns often show gradual declines over decades in places that invested in safety infrastructure, even though news reports still highlight rare disasters: a bridge collapse, a factory fire, a plane crash. This introduces a quiet but important contrast. Some types of harm decline steadily, even while our awareness of each individual incident grows, creating a mismatch between the trend and our impression of the trend. One of the most challenging aspects of reading the incident log is what might be called the reporting problem. As societies develop more formal systems, police departments, hospitals, social workers, hotlines, legal protections, more incidents get recorded that previously stayed invisible or were handled informally. Domestic violence is a prime example. For most of history, what happened within a household was considered a private matter. Husbands had legal authority over their wives in many jurisdictions. Physical discipline of children was broadly accepted. Marital rape was not recognized as a crime. There was nowhere to report such harms and often no legal framework to respond even if someone tried. Starting in the late 20th century, many countries began to criminalize domestic violence, establish shelters, create hotlines, and train police to take such reports seriously. The result in the incident log is striking. The number of recorded domestic violence cases increases dramatically, sometimes appearing to surge tenfold or more in a short period. Does this mean domestic violence suddenly became more common? Almost certainly not. It means we finally started counting it. The same pattern appears with child abuse, sexual assault, hate crimes, and workplace harassment. As awareness grows, as victims gain more support and legal standing, as reporting mechanisms improve, the log fills in with entries that were always there but never written down. Someone looking only at the raw numbers might conclude that these problems exploded in recent decades, when in fact what exploded was our ability and willingness to see and record them. Another factor complicates our reading of the log: demography. As the world's population has grown, from about 1 billion people in 1800 to nearly 8 billion today, the absolute number of violent incidents can increase even if the rate per person stays the same or falls. Imagine a country with a homicide rate of 5 per 100,000. If the population is 1 million, that's 50 homicides a year. If the population grows to 10 million with the same rate, that's 500 homicides a year. In raw headlines, 500 murders this year. The larger number sounds alarming, but the risk to any individual has not changed. The incident log needs separate columns for total counts and per capita rates, and the picture can look very different depending on which column we focus on. Urbanization adds another layer. As more people move to cities, certain types of crime naturally cluster in areas where people live in close proximity, where there are more opportunities for both crime and reporting. A rural community of 1,000 people might have 0 homicides in a decade. A city of 1 million will have some, simply because of the numbers involved. This doesn't mean cities are becoming more dangerous in any relative sense. In fact, many cities have seen dramatic crime reductions. But it means the absolute numbers can be large and the news coverage intense. Even when we've accounted for reporting changes and demographic shifts, there remains a fundamental problem with how human attention works, and this affects how we interpret the incident log. Our brains are not designed to process statistics accurately. We did not evolve in an environment where we needed to track rates per 100,000 or compare trends across decades. Instead, we evolved to notice and remember threats, especially vivid, unusual ones. A single shocking event, a mass shooting, a terrorist attack, a particularly brutal crime, lodges in memory with perfect clarity. We can recall where we were when we heard about it, how we felt, the images we saw. Meanwhile, years of ordinary safe days leave almost no trace. Thousands of times we walk down a street without incident, millions of people going about their lives without being victimized. These non-events do not register. In the incident log, long-term trends might show slow, steady declines in many forms of harm, the lines on the graph ticking downward year after year, but the spikes, individual mass casualty events, unusual crimes, highly publicized incidents, are what our brains highlight and retain. Our internal database is optimized for vividness and recency, not for accurate statistical summaries. This means that even if we had perfect access to the log, even if we studied it carefully, we would still tend to overweight the dramatic exceptions and underweight the mundane trends. This cognitive tendency is then amplified by how information reaches us. Traditional news outlets operate with an editorial logic that makes perfect sense for their purposes, but creates a systematic distortion when we try to understand overall levels of violence. News, by definition, covers what is new, unusual, and impactful. A city having an ordinary safe day is not a story. A city where crime rates have been falling slowly for 20 years is, at best, an occasional feature article. But a rare violent incident, a shooting, an assault, a terrorist attack, is immediately newsworthy. The more unusual and shocking the event, the more coverage it receives. In terms of our incident log metaphor, the news acts like a filter that passes only certain rows, high-impact entries, outliers, dramatic patterns. Everything else, the vast majority of the log, the thousands of entries that represent ordinary non-violent days and places, gets filtered out. If we consume news regularly and mistake that filtered stream for a representative sample of the full spreadsheet, the world appears vastly more dangerous than the complete data would suggest. This is not a criticism of journalism, which serves important functions in exposing problems and holding power accountable. It's simply a description of the filter and its effects on perception. This dynamic has intensified over recent decades with the rise of 24-hour news channels. In earlier eras, news was constrained by physical limitations, the time it took to print and distribute newspapers, the scheduled broadcasts of evening television news. There were natural pauses, moments when new information simply wasn't available to the public. Now, cable news networks and online news sites operate continuously. A single incident can be covered from multiple angles for hours or even days, with live updates, expert panels, eyewitness interviews, and constant speculation about implications and causes. The incident remains one row in the global log, but it receives hundreds of hours of coverage. An event that would have merited a few paragraphs in a newspaper 50 years ago now becomes an immersive multi-day media experience. We used to receive small, periodic snapshots of the incident log. Now we have what feels like a live ticker of every row flagged as newsworthy. The impression this creates is that violent events are constant, a never-ending stream, even if the actual rate of such events has not increased and may even have declined. Social media adds yet another dimension to this information landscape. Suddenly there are not just professional journalists deciding what to cover, but millions of people, each with a camera, and the ability to share what they witness with global audiences. An altercation on a street corner that no news outlet would have ever learned about can now be filmed, posted, and viewed by millions within hours. Some of these posts document genuine serious harm, others capture arguments, near misses, or isolated incidents that would have remained completely local and forgotten in any previous era. In the global spreadsheet, many rows that would have remained unobserved now get highly visible annotations and millions of views. To the person scrolling through their feed, encountering video after video of conflict, violence, and danger from around the world, it feels like the world must be descending into chaos. But to the incident log, nothing fundamental has changed about the underlying rates. What has changed is who sees which rows and how quickly the information spreads. The algorithms that determine what appears in our social media feeds add another layer of distortion. These systems are designed to maximize engagement, likes, shares, comments, time spent on the platform. Content that provokes strong emotional reactions, especially fear, anger, and outrage, tends to perform well by these metrics. If you watch a video about a violent crime, the algorithm learns that you engaged with that type of content and may show you more like it. If you click on news about terrorism or war, those topics become more prominent in your feed. Over time, each person's view of the world becomes shaped by an invisible filter that has learned to prioritize certain categories of information. For someone whose feed has learned to emphasize crime and conflict, their personal incident log becomes heavily skewed toward alarming entries. Two people looking at the same global spreadsheet might develop radically different impressions of its contents based on which rows their feeds have been trained to highlight. The algorithm doesn't care about representing the full distribution of the data, it cares about keeping you engaged. There's also a psychological mechanism at work that researchers sometimes call the availability heuristic. We tend to judge how common something is by how easily we can bring examples to mind. If we've recently seen dramatic footage of violence, a riot, a shooting, a war zone, those images are readily available in memory. When someone asks us, "Is the world getting more violent?" our brain quickly retrieves those vivid recent examples and concludes, yes, it must be, because I can think of so many instances. Meanwhile, all the non-violent interactions we had today, all the peaceful places we moved through, all the days in the past month when nothing bad happened, these have almost no mental representation. They didn't make the news, they didn't appear in our feeds, and they left no memorable trace. The incident log contains both the violent events and the vast sea of non-events, but our memory stores mainly the former. This creates an asymmetry where violence is psychologically overrepresented compared to its actual frequency. It's crucial to acknowledge, carefully and without minimizing real suffering, that the world is not uniform. The global incident log contains rows from every country and community, and the patterns vary enormously. Some nations have seen remarkable reductions in multiple forms of violence over recent decades, homicide rates falling by half or more, domestic violence laws transforming family safety, protections for minorities reducing hate crimes. Other regions continue to experience high rates of criminal violence, ongoing armed conflicts, state repression, and deep insecurity. In some neighbourhoods within wealthy countries, violence remains a daily reality, even as other neighbourhoods in the same city become historically safe. The log records all of this variation. It can be simultaneously true that certain types of violence have declined globally on average, and that specific places remain very dangerous for the people who live there. When we talk about overall trends, we're describing central tendencies and averages, not denying the lived reality of communities still waiting for those improvements to reach them. There are also categories of improvement that rarely generate headlines, but appear clearly in the long-term data. Medical trauma care has advanced dramatically, meaning that violent incidents that would have been lethal decades ago now have higher survival rates. This doesn't reduce the number of assaults, but it does reduce the death rate from those assaults, shifting some entries from the homicide column to the aggravated assault column. Public health campaigns have reduced deaths from some infectious diseases, improved maternal and child health, and extended life expectancy in many regions. Vehicle safety innovations, crumple zones, airbags, anti-lock brakes, improved road design have made travel less deadly, even as traffic volumes increased. Legal reforms in many countries have provided greater protections for children, criminalized marital rape, established rights for victims, and created accountability mechanisms for police violence. None of these changes eliminate harm, but they all reduce the landscape of danger that people navigate. In the incident log, these appear as declining trend lines on charts that almost never show up in breaking news alerts. To someone watching only the alerts, consuming only what the news filter and social media algorithms present, the world seems to be getting worse. But in the full file, several forms of risk have quietly been shrinking over decades. So why does it feel worse than ever? We can identify at least 4 major contributors, each operating independently but reinforcing the others. First, there's more complete reporting of incidents that used to stay hidden. Domestic violence, sexual assault, hate crimes, workplace harassment. As these harms become visible in the log, it can appear that they're increasing when they're actually just being counted for the first time. Second, there's the effect of larger population and denser cities, which means bigger absolute numbers of incidents even when per capita rates stay flat or decline. A headline about 2,000 assaults sounds worse than 200 assaults, even if the rate per person is lower in the larger population. Third, there's continuous news coverage and social media creating a never-ending stream of violent content, taking us from periodic snapshots to constant immersion in a curated selection of the most alarming entries. Fourth, there are our cognitive biases, the way our brains prioritize vivid recent examples over long-term statistical trends, making the exceptions feel like the rule. In the logbook metaphor, the actual table shows mixed trends, some categories declining, some stable, some rising in particular regions or demographics. But the subset of that data highlighted on our screens is heavily skewed toward alarming entries, and our minds then process that skewed sample as if it represents the whole. What does this mean for how we might read the log differently? One approach is to occasionally step back from the breaking news ticker and look at context, rates rather than raw counts, baselines rather than just current numbers, long-term trends rather than individual spikes. This doesn't mean ignoring real problems or dismissing legitimate concerns. Violence is still a major cause of suffering, and even declining rates mean real people being hurt. but placing each incident in its wider numerical landscape can reduce the sense that every headline signals a new, unprecedented collapse. When we see a news story about crime in a particular city, we might ask, what's the trend over the past decade? How does this rate compare to 20 years ago? What's the rate per capita, not just the absolute number? When we hear about a conflict, we might seek out data on overall battle deaths globally, not just focus on the one war currently dominating coverage. When we encounter reports of rising violence in one category, we might check whether that rise reflects actual changes or changes in reporting and definition. The global incident log, if we could actually see the full thing, would show us that some harms have decreased, some persist at high levels, some have shifted from one form to another, and our ability to observe and be impacted by information about violence has increased far faster than most underlying rates of violence itself. There's something deeply understandable about our tendency to feel that things are getting worse. We care about suffering, we're wired to attend to threats, and we're now exposed to more information about harm than any generation in history. Someone scrolling through news and social media on an ordinary day might encounter reports of crimes from a dozen cities, conflicts from multiple countries, accidents and disasters from around the world, all presented with urgency and emotional intensity. The sheer volume of this information would have been unimaginable to someone living 50 or 100 years ago. They might have heard about violence in their own community and perhaps major wars or disasters through delayed newspaper reports. We hear about everything, everywhere, all the time. That difference in information exposure creates a difference in perception that has nothing to do with actual trends in violence. Consider what it would be like to actually work with the global incident log in its complete form. Millions of rows, hundreds of columns, data, stretching back through time wherever records exist. You would need a team of researchers trained in statistics, criminology, public health, and history. They would spend months cleaning the data, accounting for reporting changes, adjusting for population growth, comparing methodologies across jurisdictions and time periods. They would produce reports with careful caveats. In this region, during this period, this type of violence appears to have decreased, though we have limited confidence in data before this year, and these 5 factors may explain the trend. The reports would be dense, technical, full of hedges and qualifications. They would not sound like breaking news. They would not go viral on social media. They would not provide simple, emotionally satisfying narratives, but they would be far more accurate representations of reality than the impression created by a steady stream of cherry-picked incidents presented without context. Some of the most careful researchers who work with this kind of data have found patterns that surprise people. Steven Pinker's book, The Better Angels of Our Nature, compiled evidence that various forms of violence have declined over long historical periods, even accounting for the world wars of the 20th century. This thesis has been debated and critiqued, with some scholars questioning his methodology or pointing out exceptions and ongoing problems. But even those who disagree with Pinker's more sweeping claims generally acknowledge that specific forms of violence have decreased in specific contexts. Homicide rates in many Western countries are lower than in medieval times. Interstate wars between major powers have become rare since 1945. Many forms of institutional violence like public executions and judicial torture have been abolished in most places, and protections for vulnerable groups have expanded. These trends don't mean the world is safe or that progress is inevitable, but they do suggest that violence is not an unchanging constant, and that human societies can, under certain conditions, become less violent over time. Other researchers focus on the inequalities and exceptions. Yes, homicide rates have fallen in some wealthy countries, but they remain stubbornly high in parts of Latin America and South Africa. Yes, interstate wars have become rare, but civil conflicts and insurgencies continue to devastate regions and displace millions. Yes, public health has improved overall, but pandemics, famines, and structural violence still kill on massive scales. The incident log contains both sets of facts. It records improvements and persistent horrors side by side. The question is not whether violence exists, it clearly does, but whether our subjective sense of living in an especially violent time matches what the full dataset shows. There's also the question of what we compare the present to. If we compare today's world to an imagined ideal where no violence exists, everything looks terrible. If we compare it to the world of 50 years ago, or 100 years ago, or 500 years ago, Using the best available data for comparable categories of harm, the picture becomes more complex. Different types of violence follow different trajectories. Genocide and mass atrocities, for instance, did not decline smoothly through the 20th century. They peaked horrifically in several periods and continue to occur, even if international mechanisms to prevent and respond to them have improved. Terrorism, by some measures, has increased in recent decades, though it remains responsible for a small fraction of violent deaths globally compared to interpersonal violence and conflict. Sexual violence and gender-based harm remain widespread and underreported even with better reporting systems. The log doesn't tell a simple story of linear progress. It tells complicated, interweaving stories of different harms rising and falling in different places and times. What remains consistent is the gap between perception and trend. Surveys consistently show that large majorities of people in many countries believe crime is rising nationally, even when data shows it falling. People estimate that their risk of being victimized is much higher than actual crime statistics suggest. When asked whether the world is getting more or less violent, most people guess more violent, even in periods and places where multiple measures of violence are declining. This gap is not because people are stupid or irrational. It's because the information environment has changed more dramatically than the underlying phenomenon. We've gone from knowing little about violence outside our immediate community to being flooded with detailed, emotionally intense information about violence everywhere on Earth, presented in ways that maximize engagement and emotional response. Our perceptual systems, evolved for a small group environment, cannot intuitively correct for this flood of curated information. The result is that we feel less safe even as many of us have become statistically safer. There's another dimension to consider when we think about the incident log and our relationship to it, the psychological weight of knowing. In previous centuries, a person might have been deeply affected by violence that occurred in their own village or town, but they would have been largely unaware of violence happening simultaneously in distant places. Their circle of concern was limited by the bounds of available information. Today we carry in our pockets devices that can instantly inform us of suffering anywhere on the planet. A bombing in the Middle East, a shooting in another country, a natural disaster halfway around the world, all of these become part of our emotional landscape within minutes of occurring. In the incident log, these are simply additional rows in their respective geographic and categorical columns. But to our nervous systems, each notification can trigger a stress response, a moment of empathic distress, a flash of anxiety about the world we're living in. The cumulative psychological burden of this awareness is something humans have never had to carry before. This raises questions about the optimal level of awareness. On one hand, global connectivity and information sharing have enabled remarkable humanitarian responses, international cooperation, and pressure on bad actors who might once have operated in obscurity. When violence occurs, the world can know about it quickly, and resources can be mobilized. Injustices that were once hidden can now be exposed and challenged. The incident log becoming more visible and complete is, in many ways, a moral achievement. But on the other hand, there's a point at which constant exposure to global suffering may not make us more effective at reducing it, and may instead lead to compassion, fatigue, anxiety disorders, or a paralyzing sense of helplessness. Finding the balance between informed awareness and psychological sustainability is a challenge that previous generations never faced. The incident log also intersects with questions about how we measure progress as a civilization. If we define progress primarily through economic metrics, GDP growth, technological advancement, increased consumption, we might overlook trends in violence and well-being. But if we include measures of safety, reductions in various forms of harm, expansions of rights and protections, then many societies show considerable progress over time, even if that progress is uneven and incomplete. The log provides one set of metrics among many for asking whether things are getting better or worse. It's not the only measure that matters, but it's one that speaks directly to basic human concerns about safety and suffering. Different philosophical traditions would interpret the log differently. A pessimistic view might focus on the persistence of violence despite centuries of moral philosophy and religious teaching, seeing the continuing entries in the log as evidence of unchanging human nature. An optimistic view might emphasize the declining rates in many categories as evidence that human nature is not fixed, and that social arrangements can reduce violence. A tragic view might see both the progress and the persistent suffering, acknowledging improvements while recognizing that violence seems to be an enduring feature of human society that can be reduced but perhaps never eliminated. The log itself doesn't adjudicate between these perspectives. It simply records what happened and allows different observers to draw their own conclusions about meaning and trajectory. There's also the temporal dimension to consider, the way violence clusters in certain periods and then recedes. The 20th century, despite its overall trends toward reduced violence in some categories, contained extraordinary spikes. The World Wars, the Holocaust, Stalin's purges, Mao's Cultural Revolution, the Rwandan genocide, the Khmer Rouge killings in Cambodia. These events represent some of the darkest entries in the entire historical log, moments when organised violence reached industrial scales. Yet these same decades also saw the establishment of international human rights frameworks, the creation of institutions designed to prevent genocide and war crimes, and broad expansions of civil rights in many societies. The log records both the horrors and the responses to those horrors, the ways that catastrophic violence sometimes catalyzed efforts to prevent its recurrence. This pattern, violence triggering reform, appears throughout the log. Major workplace disasters led to safety regulations. Epidemics of drunk driving deaths led to stricter laws and enforcement. High-profile cases of domestic violence led to legal changes and support services. School shootings, though they remain statistically rare, have prompted debates about gun control and mental health services. In each case, a spike in the log, especially if it receives significant attention, can mobilize political will for prevention efforts. The question is whether we need such spikes to drive change, or whether we could be more proactive based on the trends we can already see in the data. Can we read the log carefully enough to intervene before the dramatic outliers occur? The methodologies used to compile the log have themselves evolved and become subjects of study. Criminologists debate the best ways to measure crime, including what should count as a criminal incident and how to account for dark figures, crimes that never get reported. Epidemiologists studying violence as a public health issue bring different frameworks and metrics than law enforcement agencies. International relations scholars tracking conflict use databases with specific criteria for what constitutes an armed conflict, and these criteria can affect the patterns we observe. The incident log, in other words, is not a simple objective reality, but a constructed dataset shaped by the definitions, methodologies, and priorities of those compiling it. Different versions of the log using different standards might tell somewhat different stories. This constructed nature doesn't make the log useless or purely subjective, but it does mean we need to read it with awareness of how it was assembled. When we see a change in the numbers, we should ask whether the change reflects reality, or a change in methodology or reporting. When comparing across countries, we need to know whether they're using consistent definitions. When looking at historical data, we need to acknowledge the greater uncertainty in earlier periods. The incident log is our best effort to quantify patterns of human harm across time and space, but it's an imperfect tool used by imperfect observers trying to understand a complex reality. As we think about the future entries in this log, the rows that haven't been written yet, we face questions about what's controllable and what isn't. Some forms of violence are tightly linked to social conditions that can be changed. Poverty, inequality, weak institutions, lack of opportunity, untreated mental illness, easy access to weapons, cultures that glorify violence or devalue certain lives. Other forms seem more random, more resistant to prevention. Crimes of passion, sudden psychological breaks, accidents despite safety measures, conflicts that erupt despite diplomatic efforts. The log will continue to record both preventable and seemingly unpreventable incidents. The challenge is distinguishing between them and focusing resources where they can make the most difference. Technology adds new categories to the log while potentially reducing others. Cybercrime represents a form of harm that barely existed a few decades ago. Now it requires its own columns, tracking financial losses, data breaches, harassment and exploitation that occur in digital spaces. Autonomous weapons systems raise questions about future forms of warfare that might generate new types of entries in the conflict sections. Meanwhile, advances in surveillance, forensics, and emergency response may help prevent or quickly resolve incidents that would have had worse outcomes in earlier eras. The log of the future will look different from today's log, even as it continues the same basic project of trying to measure and understand human harm. One aspect of the log that deserves particular attention is the prevention column, a hypothetical section where we might track incidents that didn't occur because of successful interventions. This is necessarily speculative and hard to measure, but it's crucial for understanding the full picture. How many potential suicides were prevented by hotlines and mental health services? How many domestic violence situations were diffused by early intervention programs? How many conflicts were resolved through diplomacy before they escalated to armed conflict? How many crimes were deterred by effective policing and social programs? These non-events don't make news, don't generate dramatic footage, and don't lodge in memory, but they might represent some of the most important entries in a complete log of violence and its prevention. The challenge is that we can never be certain which specific incidents were prevented. We can only observe overall rate changes and infer that prevention efforts played a role. There's something both sobering and hopeful in the idea of this vast spreadsheet. Sobering because even with all the progress in some categories, the log still records enormous amounts of suffering every year. Every number represents a person who was hurt, a family that experienced loss, a community that was traumatized. The abstraction of statistics can make us forget the human reality behind each entry. But there's also something hopeful in the concept of the log, the idea that violence is not an unmeasurable chaos, but a phenomenon we can study, understand, and work to reduce. The very existence of the log, real or metaphorical, represents a commitment to not simply accepting violence as inevitable, but instead tracking it, analysing it, and learning from patterns over time. As tonight's examination of the incident log comes to a close, imagine those shelves of thick binders, each one filled with neat columns of numbers, homicides by year and region, war casualties by conflict type, reports of domestic violence since systematic tracking began, traffic fatalities before and after seatbelt laws, workplace injury rates over decades of regulatory change. Imagine the people who maintain this log: epidemiologists, criminologists, demographers, historians, all of them trained to read data with caution, to note when definitions change, to account for reporting biases, to resist the pull of dramatic anecdotes in favour of systematic evidence. They debate methodologies in academic journals. They revise estimates when new information emerges. They acknowledge uncertainty when data is sparse. They know that every number in their spreadsheets represents a real person who suffered, but they also know that understanding overall patterns requires stepping back from individual cases to see the larger shape. The world may not be perfectly safe, it certainly is not, but in the log, danger becomes something we can count, study, compare across time and place, and slowly learn to reduce. It's not an unmeasured storm, not an overwhelming chaos, not a spiral into unprecedented darkness. It's a complex set of phenomena, each with its own patterns and causes, some improving, some worsening, most varying by location and context. The gap between how it feels and what the numbers show is itself a phenomenon worth understanding. Not to dismiss our feelings, which are real and valid responses to the information we encounter, but to recognise that those feelings are shaped by an information environment that has changed radically, while many underlying risks have not changed in the ways we imagine. When you encounter news of violence tomorrow, or next week, or whenever the next alarming story appears in your feed, you might recall the image of that vast spreadsheet. You might ask where this particular incident sits in the larger columns and rows. Is it part of a trend or an outlier? Is this type of harm increasing, decreasing, or fluctuating within a long-term range? Has reporting of this category changed, making comparisons difficult? Are we looking at a rate or a raw count, and does the distinction matter? These questions don't diminish the suffering of those involved in the incident, but they do provide context that can prevent one incident from feeling like evidence of total collapse. The log is always being updated, new rows added each day, but its overall shape changes slowly. Most changes are incremental, visible only when comparing data points years or decades apart. The dramatic visible changes are almost always in our information systems, our ability to see, share, and be affected by news of violence, rather than in the underlying rates themselves. So as you drift towards sleep tonight, you can let go of the sense that the world is uniquely, unprecedentedly violent in this moment. The spreadsheet tells a different story, more nuanced and in many ways more hopeful, even while acknowledging genuine problems that persist and demand continued attention. The real epidemic of our time may not be violence itself, but our exposure to curated information about violence, presented without context, optimized for engagement rather than understanding. The log remains, patient and detailed, maintained by careful people who know that truth emerges not from headlines, but from long columns of numbers compared thoughtfully over time. That's the story recorded in the binders on the shelf, waiting for anyone who wants to read past the breaking news ticker and see what the longer record actually shows. The next story is about to begin. Please relax and enjoy.